Welcome to your daily dopamine with Dr. Joe McCullough, where we deliver daily doses of education, entertainment, and
pointing towards that, but you can turn around.
Back, relax, and get ready to be dopamine. Oh, yeah.
All right. Welcome to your daily dopamine. Today is episode 2 of our weekly series, Ask a Physicist Anything with Paul Graham. So today we're continuing with 2 topics. Let me actually move this up a bit. 2 topics we didn't get a chance to finish last week, questions people had, and then we will answer any questions you have. So what we were talking about, people wanted to know about quantum entanglement and the physics of Interstellar. How realistic was it? So let me just say, Paul and I disagree. I really liked Interstellar. I thought it was an interesting movie. I thought that I was into it. And the physics, although not perfect, there was some interesting physics that they touched on. You loved the movie, awesome. And Paul is going to talk a little bit about the physics of Interstellar. I'm actually working on a Periscope show just on entanglement. Who is that? Oh, Fine Woman. Awesome. So there's an awesome physicist here that does her own show. And I've caught her before. Okay, so let me turn this around and give you to Paul. Hey, Paul.
Hey there. All right, so I did catch Interstellar this week, or at least I caught about 2/3 of it. It's a very long movie, I realized, which is not a bad thing in itself.
Let's talk about a few things specifically.
Okay.
I think a lot of people want to know about, is the time dilation realistic, where they're going down to a planet, aging a lot less than the people that are staying up in the spaceship?
Okay, kind of. I mean, it can happen. It just can't happen quite the way they portrayed it in the movie. But yeah, general relativity, which is a very well-tested model. We watch neutron stars orbiting around one another and everything like that. There's enough astronomical data on what happens in these real high gravitational fields that, yeah, we know general relativity is right. And by the way, when I say it's right, I don't mean it's the last word on anything. Almost nothing that we have in physics is the last word on anything, but I mean it's a better approximation than the models that came before it. General relativity is a lot closer to right than Newtonian gravity. It works under a much broader variety of circumstances when you get into the really dense masses like neutron stars and black holes, when you get into the really powerful gravitational fields. Newton's model of gravity doesn't come anywhere close to giving you the right answer. General relativity does. By the way, for weak gravitational fields, like the one that we're standing in right now, that's nowhere near the intensity that you'd get if I was near the event horizon of a black hole, in these gravitational fields, Newton's laws and general relativity agree with each other out to, 12, 14, 16 decimal places, depending on just how weak the field is. But if it mattered, if you really could measure out to that many decimal places, even there, general relativity is more accurate than Newton's gravity. So it's not like, there's a realm that GR doesn't work.
And in fact, you have to take into account general relativity for GPS
For
satellites.
things like GPS satellites, absolutely. The frame dragging as the Earth rotates has been verified. So yeah, general relativity is an awesome model. The place where we know it fails is if you keep ramping it up to even higher energy, even more intense fields, then eventually general relativity and quantum field theory start contradicting each other. So if you go up to a high enough energy density, then presumably both of these models are just low energy approximations to some even deeper, even better model. Same way that Newtonian physics was a low energy approximation to relativity and quantum mechanics. Now, as far as the time dilation they talked about in Interstellar, all right, it is true. The deeper down you go in a gravity well, and when I say gravity well, I simply mean if you go downward in a gravitational field. So we are standing in a slight gravity well right now. It's the gravitational field of the Earth. We got to climb out of this to get into orbit around the Earth, or better yet, to escape from the Earth, go to the moon, send probes to other planets or the outer reaches of the solar system. We got to climb out of the Earth's gravity well.
So Paul, quick question. So would that mean technically that I age at a different rate as I'm on a plane? I'm on the surface of the Earth.
Yes, and it is even measurable. If you send a really good atomic clock up on that plane, you can measure the difference, both from that and from the time dilation, just from the fact that the plane is moving fast. Now again, it's moving at a tiny fraction of the speed of light, so you'd barely notice it. But yeah, you do age slightly slower on that plane because of the speed, but then you also age slightly faster because you're higher up in the gravity well.
And we're talking on the order of nanoseconds or less, correct?
Nanoseconds per day would be about right, yeah.
So nanosecond, 10 to the minus 9 seconds for those of you not actually studying physics. So real quick, while Paul is drawing that, my name is Joe, and we are doing Ask a Physicist Anything every single Wednesday. I'm the program chair at Cabrillo College in Santa Cruz. Paul is one of our awesome instructors, and we are just here talking about physics, answering questions. People had questions last week about quantum entanglement and the physics of Interstellar. We're going to touch on those. We're trying to keep this to about a half hour. So we'll spend a few more minutes on this and then touch on quantum entanglement and then ask any questions you have. All right, Paul, take it.
All right, so even these people sitting here on the Earth, they are experiencing time passing at different rates. The person on the ground, her wristwatch is ticking slower. I like the scene where the guy tried to give his daughter a watch and they synchronized it, and he said, you know, let's check how these look relative to each other when I get back. Thought that was a cool scene. But yeah, the person on the ground, time's passing slower. The person who is standing on this platform, time is passing slightly faster. Person who's off here very far from the Earth's gravity well in the first place, back there the time is passing kind of at the background default rate that you get for most of the universe. So this person is seeing the fastest rate of time passing out of any of the three of them. However, because the Earth's gravitational field is so weak, you're not getting a major difference. Like Joe said, nanoseconds per day is probably on the right order. So you're, the time's passing slower here. You're going to have to make a very detailed measurement to even notice it. Now, if on the other hand you go near a black hole, by the way, that black hole in the movie, they called it Gargantua or whatever, I don't know where the hell it was supposed to come from. Actually, I have to admit, I think I did admit, I've seen most of the movie, but not yet all of it. So they could answer this question at the end.
They don't answer where it came from.
Okay. If it was just a collapsed star, it would be a hell of a lot smaller than that. It would be about 100 kilometers across. So the fact that it was this big thing, bigger than the planet that was orbiting it, I don't know where the hell that came from, but that's a big black hole. That's many star masses together there. Now, if you were to start out standing far away from that, so you're watching time pass at the background rate of the rest of the universe, the big flat expanse of space out there, as you descend toward the black hole, yeah, time is going to pass slower and slower until if you're hanging out right here outside the event horizon, the rate at which time passes goes to zero. The ratio between time out there and time here goes to infinity. So yeah, as you hit the event horizon, if you're looking back at the rest of the universe, you would essentially see the entire history of the universe go by in what seems to you an immeasurable short time as you stand there with your eyeball right on the event horizon.
But let's just say you probably don't want to hang out near the event horizon of a black hole as a general rule.
Yes, well, there are tidal forces. Now, it is a myth that says you will automatically be ripped apart by tidal forces before you reach the event horizon. You will be before you reach the singularity at the center, that infinitely dense point at the center. And by the way, when I say infinitely dense, well, actually there's a good chance it isn't, because again, general relativity would break down as I approach that energy density. So I don't know what the real answer is, but I also don't have any confidence that the real answer is literally infinite density.
Spaghettification.
Yes, but before you get there, spaghettification exactly will be an issue.
Long time
this
to
poor
get
guy
there.
down here who's fallen past the event horizon toward the singularity, the gravitational pull on his feet is so much more powerful than the gravitational pull on his head that yes, spaghettification is the word for it, and anything beyond that would be too gruesome to describe. Yeah, he's not going to finish that trip to the event horizon. Neither will a proton. It will get ripped apart into constituent quarks before it reaches that, I'm sorry, not the event horizon, before it reaches the singularity. My whole point was, hey, you can survive the trip past the event horizon. The bigger the black hole is, the more minor the tidal forces will be outside the event horizon. So that giant black hole that they had, actually you could probably, I imagine, fall past the event horizon of that one and still survive that part of the trip, although the singularity would be a problem. Now, if you've got this planet which is orbiting rapidly around the black hole, one problem is going to be, is the planet itself going to be ripped apart by tidal forces? Because again, the gravitational pull on this side of it will be a lot more powerful than the pull on that side. And that might be enough to rip the thing into gravel. Assuming that doesn't happen, and that planet seemed to be like, surviving very nicely for such a precarious place. The problem is, okay, what they said while they were still out here on board their spaceship was 1 hour on the planet equals, was it 2 years or 7 years?
Something like that, 2 years, or 7 years.
2 years out in the rest of the universe, including for the poor guy who was left on board the spaceship.
Or I think it might be 7 years, something like that.
Was it 7?
It was a long time.
I know he ended up waiting for them for, well, I guess spoilers are okay, since but he waited for like 23 years or something. But beforehand, was it 7?
Yeah.
Okay. Now you look at that. That's a ratio of tens of thousands or more to 1 there, which means that they are so damn close to the event horizon that, well, number one, they're going to have a hard time climbing back out of that gravity well. If you're so close to the event horizon that time is passing for you 10,000 to 100,000 times slower than for the rest of the universe, which is what that ratio comes to, you're going to have, the amount of energy it'll take you to climb out would be about enough to go up to what they call a gamma factor of 10,000 in special relativity. What that means is you will be traveling at a string of about 10 nines times the speed of light. Now, if their spaceship has enough fuel to get itself out of that gravity well, then it's got enough fuel to get up really close to light speed, which all of a sudden means that clunky little journey they took out to Saturn at slower than light speed, about like a modern spaceship does, looks real incongruous compared to the feat of climbing out of that well. The other thing that was kind of weird is they say, okay, well, here's our spaceship parked right out, in orbit around the black hole right above the planet. For some reason, no time dilation's happening on the spaceship, but once you go down to the planet, it all is. And, that part didn't make... The closer you get into that black hole, the slower time will be passing for you. They didn't leave their spaceship parked clear the hell out there somewhere. They left it parked right outside the orbit of the planet. The guy in the spaceship, well... I guess that would be good news for that character. He's not going to have to wait for them for 23 years. Even if it was 23 years back on Earth, maybe it was... 3 hours for them, maybe it will be 3.5 hours for him. So in other words, it's a smooth thing. It's not a sudden transition. They talked about a cusp that you cross, which is where the time dilation kicks in. There's no cusp. There's this smooth transition.
You're saying it was the distance to the spaceship. Fine woman, I did not catch that.
Okay.
I'm wondering if we want to move on to quantum entanglement.
Okay.
Or do you want to finish this?
She didn't catch which part?
She was saying I didn't catch it, but she thought it was something about the distance to the planet that was the issue.
Yeah, well, they did even mention, he asked them, how far above the planet do I have to be for this time shift not to kick in? And they said, well, you have to be right outside that cusp. Now, they were pointing to something off screen when they said that cusp. But they made it sound like there was some kind of sharp transition between the fast time zone and the slow time zone. Again, it's not a sharp transition. It just gradually time gets slower and slower as you descend toward that event horizon. But, I mean, the basic idea that time passes slower when you're deep in a gravity well, hey, that was cool. They brought in Kip Thorne to consult on the movie, which I thought was kind of awesome. Kip Thorne's a big-time general relativity guy from way back who works at Caltech. So they had all the right talent in place, and I won't blame Kip for the little bits that went wrong. I imagine that's kind of the process of communication from the consultant to the script people to everybody else.
Hey, check it out. We got his book.
Kip Thorne.
Great book by Kip Thorne.
Black
Holes and Time Wars.
I read your book. Okay, no, that's somebody else. But this is like a public level book, right?
It is. It's kind of along the lines of Stephen Hawking.
Yeah. Kip Thorne's awesome. I have not read this myself, but I would recommend it just based on the stuff by him that I have read.
Okay. Can you give us... So for those of you just tuning in, my name's Joe. This is Paul. We're doing our weekly Ask a Physicist Anything. Last week we had some questions on Interstellar we didn't get a chance to touch on. And actually somebody wanted to know about quantum entanglement. Although the question wasn't really well formed. It was just, talk about quantum
Well,
entanglement.
I figure we could get the basics down, and then we can kind of talk about what are some of the applications where you could go beyond that.
Can you do
We
that
don't
in
have
10
to
minutes?
Do them all this.
Okay.
But okay.
Trying to keep this to 30 minutes, so actually we're not actually answering any new questions today.
But give
I
us
will
new questions so we can research them for next week.
type in questions that you have. I will go through the comments sometime this week and then see if Paul wants to touch on any of those next week. Okay, quantum entanglement. Take it, Paul.
All right. So, losing our black hole. Where did it go? So the idea behind quantum entanglement. Now, first, somebody asked last week specifically what kinds of technology can this be applied to. Everything, I mean, quantum computing, quantum communication, aka quantum cryptography, all of the kind of more exciting direct applications of quantum mechanics these days, a lot of those are based on this entanglement idea. So we can go deeper into any of those topics in the future if anybody requests it. The basic idea of entanglement, though, goes way back to the heyday of quantum mechanics in 1920s and 1930s. In quantum mechanics, if I'm going to describe a particle, an electron, say, about as humble a particle as there is, I don't do what Newton would have done, which is tell its trajectory, tell where that electron is at each moment in time. Instead, I solve the Schrodinger equation. Now, the Schrodinger equation is the old-fashioned non-relativistic version of quantum mechanics. There's lots of iterations that have come since then. But the Schrodinger equation describes that electron as this fuzzed-out probability wave. This has a lot of implications. At any given moment, there is no correct answer to where that electron is. I'm not just saying that humans don't know where that electron is. I'm saying nature doesn't know where that electron is. The correct answer for what's that electron doing is to quote off this probability wave that says, actually, if you look for it, you got a strong chance of finding it in this region. You've got a weaker chance of interacting with it over here. Maybe there's a node in the probability wave along here where you have zero chance of interacting with it. But it could manifest in any of those places. And in fact, you could say nature has not made up her mind until you actually run an interaction, try to interact with that thing, and find out what happens. Now, that is odd enough and non-intuitive enough. And the fact that it's a non-deterministic theory is the thing that led Einstein to give one of his famous quotes on quantum mechanics when he said, "I can't believe that God would play dice with the universe." Now, if he were alive today, I don't know if he would retract that statement, because it really does seem like that non-deterministic nature of quantum mechanics is here to stay. By the way, when they say Einstein was a opponent of quantum mechanics, he wasn't saying that we should go back to Newtonian mechanics. He was saying, as we move forward, as we learn what the deeper models are that lie behind quantum mechanics, he was laying a bet that, hey, it'll turn out to be deterministic after all. Now, that has not happened, and in fact, it's looking less and less likely that that ever will happen. I imagine Einstein would probably be singing a different tune today, but he's not around to ask, so I can't speak for him. But one of the odd things that he pointed out that comes out of this wave function is if I have two particles interacting, could be two electrons, could be two photons, let's make it two electrons, and I let them interact tightly with one another, so there's this tied up knot of probability fluid here that's the electrons, and then they go flying off in opposite directions. If the total amount of spin, the total amount of angular momentum in this original knot of entangled particles was zero, then as the electrons go off, one of them might end up, well, one of them will, if I measure how much they're spinning around any given axis, say the z-axis, one of them will be spinning counterclockwise as viewed from above. We actually use the right-hand rule and we call that a spin-up particle. So I'm going to draw it as an up arrow. The other one will be spinning clockwise if viewed from above, and we call that a spin-down particle. Or it could be the other way around, but it's got to be one of each. If there was no angular momentum to begin with, they can't suddenly have a total angular momentum. So if this guy's spinning this way, this one will be spinning the other way, and vice versa. Now, that can be one of those issues that nature has not yet decided. So now nature is in the superposition of states. If this guy's spin up, this one must be spin down. Or the other possibility is this one is spin down and this one is spin up. The whole system can be in a superposition. It could be 50-50, it could be a different set of odds, but where it might be in this state and it might be in this one. The thing that Einstein pointed out was, okay, that means those particles are now permanently entangled. And he used this as one of his arguments that quantum mechanics could not be self-consistent. Again, he wasn't saying let's just throw it away and go back to Newtonian mechanics, but he was saying, hey, let's keep on pulling at this loose thread, because I bet this will be one of those moments when that loose thread makes the whole tapestry fall away, and there is something new and marvelous behind that. And his opinion was it would be a deterministic theory without spooky action at a distance, as he liked to call this. But his point was, let these things go for 10 light years if I want.
Paul, somebody just said you're terrific. Is he not awesome? I'm doing this whole weekly series just so I can hear Paul explain complicated stuff every day. All right, sorry, go Paul.
Oh yeah, so Einstein's thought experiment on this was he said, I can wait until these things are, many light years apart. Not that we have two labs many light years apart right now, but that's why it's a thought experiment. And he said, no matter how far apart they get, if I finally get around to having somebody in lab B measure the spin of this one, and she finds that it's spin up, well, then immediately she knows that her colleague over here in lab A is going to measure that this one is spin down.
Even if they're infinitely far apart.
No matter how far apart they are. And not only does she know that, the universe now knows that. When I was saying that nature itself doesn't know which particles spin up and spin down if it's in the superposition of states, well, Einstein was saying, our humble scientist makes a measurement over here, and now nature knows, the universe knows, that this particle over here must be spin down. Einstein saw that as a form of cause and effect, or information transmission. He said that the measurement this person makes over here has now affected the state of this particle. This one is now spin down when it used to be in a superposition. And he said, hey, you got a choice. Either you believe that quantum mechanics is kind of an incomplete approximation, and that doesn't really happen, or you believe that information can be transmitted faster than light. And he said, I'm the one who came up with relativity, said that it couldn't, but I mean, hey, I could have been wrong about that. But make your choice. You can't have it both ways. Either you got to stop believing in special relativity, or you've got to agree that quantum mechanics is this incomplete approximation that still has a lot of room for improvement. Now, quantum mechanics did still have a lot of room for improvement, still does, but not necessarily along the lines Einstein was talking. What most of the physics community ended up doing, now whenever Einstein came out with one of these thought experiments...
Just pause for 1 second. For those of you joining, quick question. We are talking about quantum entanglement. It was a question we had last week and didn't have a chance to cover. So Paul's going through quantum entanglement, what exactly that means, in hopefully under 10 minutes or less. But Paul gets excited, so we might be here for a couple days. Actually, no, only another about 10 minutes maybe.
All right.
And then real quick, if anybody has questions, we're not actually answering them right now just because we're going through quantum entanglement. I will go through the replay, check out the comments, pull out some questions that we can touch on next week. All right, continue, Paul.
So what most of the physics community ended up doing about this, they took Einstein's objection seriously, like they took most of Einstein's thought experiments seriously. He was damn good at coming up with a brilliant way of illustrating, possible weak points in a model. But they decided, let's take a third option. It's not that we don't believe in relativity. It's not that we necessarily believe that quantum mechanics is wrong. But let's take a closer look at what we mean by the state of this electron. All right, so we started out saying the universe was in a state where either this guy was up and this one was down, or this one was down and this one was up. A moment later, after physicist B makes her measurement, we are now in a state where this possibility has been crossed out. And we know for a fact, and we figure the universe knows also, that the electrons are now spinning like this. This one's spinning counterclockwise, this one clockwise. Does that mean we actually had a physical effect on this electron over here? It'd be weird if we did, because the experimenter who made that result is like 20 light years away. It's supposed to have happened instantly. What most of the physics community ended up saying was, no, that doesn't actually count as transmitting information. There is no way that this guy over here in lab A can use that to receive a message from physicist B. Yeah, when he makes his measurement, he gets that the electrons spin in this way. But he doesn't have any way of knowing, was he the first one to collapse the wave function, as they like to say? Or had she already collapsed it over here? He already had a 50-50 chance of getting this one to be spin up. And even if physicist B has already made her measurement, still half the time she's going to get spin down and he's going to get spin up. The other half the time, even if she's the first one to make the measurement, she gets spin up, he gets spin down. If he's sitting over here in his lab, all he knows is, hey, if they keep repeating this experiment again and again, half the time he gets spin up, half the time he gets spin down. This electron still behaves exactly the same way to every measurement he can make. If we want to say mathematically, B has already collapsed the wave function with her measurement, there's no way A can tell the difference. So she hasn't really sent him any information. What this meant is people really backed off on the idea that the wave function is a real thing, and they said, okay, the wave function's our best mathematical description of reality, but it's not an actually physically real thing. You can't measure a wave function, you can only measure the properties of this particle. And if you think about it that way, then you'd say, nah, no information was sent faster than the speed of light here. The whole issue that we're talking about is called the EPR paradox. The three people who wrote this paper, which was the shot across the bow of the physics community, were Einstein, Podolsky, and Rosen. And they wrote the paper saying, hey, this would represent faster than light information transmission. You got to live with the implications of that. The rest of the community, after a long period of saying, oh, what the hell are we going to do about this, kind of settled on the idea of, okay, thanks for pointing that out. We really were talking way too much like the wave function is a real measurable thing, but it's not. And you have not actually communicated any information, even if this thought experiment works just like you said it did. So it kind of changed the way people thought about quantum mechanics, but it didn't actually cause people to say quantum mechanics is fundamentally inconsistent, and it didn't cause people to say you can send information faster than light. Now, we have brought that whole question of quantum entanglement up to the dizzyingly recent years of the 1930s now. There's a hell of a lot that we could say about it beyond that. Again, we can go into the applications these days in quantum computing. We can go into quantum cryptography. We can talk about the reason why, when I was saying, hey, Einstein lived up to the 1950s. If he had lived up to the present, he probably would have changed his mind on this whole determinism issue. I can tell you the reason for that, which was a whole line of argument called Bell's theorem that was kind of playing itself out in the 60s and 70s. So there's lots more directions we can go with quantum entanglement. Give us I've given you only the way the field started here, but yeah, give us your questions. And on one hand, I feel like, oh man, I haven't told them a damn thing. There's so much more we could do. On the other hand, I know Joe said we would keep this to a reasonable amount of time, so I don't want to try your patience. So I will just say, consider this nothing but an opening introduction to the field. This won't be all quantum entanglement all the time, but this is something that we can definitely follow up on further things.
Let's move this to a bar, somebody suggested.
Yes!
And Julia, fine woman, said she might be doing a scope on quantum entanglement. Julia,
Yes.
if you are out there I'll buy first round, let me know, because if you're doing a scope on quantum entanglement, I would love to catch it.
Yeah, I would love to see that
Have
also.
you discussed Interstellar? Yes, we did discuss Interstellar at the beginning. And if you missed it, you can catch the replay.
And if you got further questions on it, we can come back to that also.
And we could definitely, but I definitely want to be able to field questions and not always be doing questions from last week.
Previous, yeah.
So I'm going to turn this around.
Thank you for joining us. We are going to do our best to keep these in 30-minute, 35-minute blocks. Again, my name is Joe. This is Paul.
Hi there.
We both teach at Cabrillo College in Santa Cruz, California. We both teach physics and love physics, and I started a weekly series, Ask a Physicist Anything, so I could hear Paul talk about all sorts of awesome topics.
All right, this has been fun. We look forward to hearing from all of you again next week, and thank you for the questions. Sorry if my answer was inadequate, but help me figure out what to focus on, and we will come back to this.
Yes, and I am feeling better, thank you. And tomorrow, for those of you who are following me, I am doing part 3 of a 3-part series on how to read faster. Basically, how to double your reading speed using just 5 simple techniques. Really useful for going from about maybe 200, 250 words per minute up to 500 words per minute.
I just skip every other word.
Or skip every other word. You triple your reading speed by just reading every third word, and you get more comprehension somehow. Okay, Thursday, finishing up speed reading. Friday, I'm going to show you one of my favorite demonstrations, show you how you can freeze a wave, Matrix style. And then Spreeder.com is awesome. Yeah, so anybody who's interested in how to double your reading speed, check that out. Tomorrow it'll be about 3 or 3:30, 4 o'clock Pacific Standard Time. And also I am archiving all of these on my YouTube channel. Just search for Joe McCullough. I'll archive this one this afternoon. So that is it. Thank you for all the hearts. Thank you for tuning in. And if you're interested in more awesome physics, we're here every Wednesday, 3 o'clock Pacific Standard Time. Bye from Elkton. Well, thank you, April. And yeah, everyone who's joining, I appreciate it. My name is Joe. Bye. It's hard to see the camera. Camera's right over there. Okay. Thank you for joining. I'll catch the replay. Awesome. All right. Have a wonderful afternoon and hope to catch you all sometime this week. All right.